Copyright in these lectures is either owned by the ANU or a third party who has licensed the ANU to use it. Students may use the recording for personal study only. No lecture may be communicated online, copied or shared without the prior permission of the ANU.
What is it doing? Okay. Alrighty, so let's get started. Alright, so today I was going to go through a couple more, at least, examples of time series analyses, and again, just try to stress that the process for the time series stuff, at least as far as we're concerned, is following a series of fairly concrete steps that will generally get you where you want. With two comments, both of which I've made before. The first is that remember that, you know, throughout, even with these steps, which appear to be concrete, there are always choices to be made, and you'll make those choices. So, you know, you can take the same set of steps as someone else and you might end up with a different model because you've taken choices throughout that process. That's okay, remembering that all models are wrong. Some models are better, some models are worse, okay? So keep that in mind. The other comment that I've made before, and it's worth making again, is that we're pursuing here a very limited range of time series models. Okay, so we're not, for example, considering any moving average models. So we're really restricted to short-run autoregressive models. So it's possible, and one of the data sets we'll look at today, a long-run AR model doesn't fit it particularly well. But, you know, we're sort of in this space where in this course we cover a lot of stuff at a fairly shallow level in terms of the methodology, the focus being on the graphics. If you want to learn more about time series, then you really need to do a course on time series, you know, of which we do have one. People have this fantasy about time series that if they understand time series well enough, they'll be able to beat the stock market. No, no. All of the time series models that you learn, even in an advanced time series course, can't hope to deal with some of the issues that stock markets have, which generally, I mean, the principal one being the uncontrolled heteroscedasticity or volatility, as they like to call it in finance. So, you know, a couple of weeks in GDA and you won't be beating the stock market, I'm afraid. So, oh well. All right, so we're going to look at a few data sets. The first data set we're going to look at is a very famous data set, actually. It's carbon dioxide emissions from a volcano in the US state of Hawaii, Mauna Loa. And this volcano has been doing stuff very, very regularly for a very long time. So we have a data set, I'll just type it here, CO2. This is the data set that's built into R, and you can see it's monthly carbon dioxide emissions from January 1959 all the way up through 1997. Okay, and I presume in some future version of R they'll just keep on continuing the data because the data's being collected, but every so often they say, well, this is the data set. So we have these monthly emissions, and we need to try to understand the series. Now, I got an email yesterday which was good, asked a good question. The question is, what's the point of time series modelling? It's a very general question, but it's the reason that the question comes up is because regression modelling seems, at least in some sense, to have a point, right? And that point is typically, well, I've got a bunch of x's and I want to understand a y. How does that relationship work, and how do I understand y as a result of that? And time series is fundamentally different because you still have x's and a y, it's just that the x's are all time, right? And y is the series that you're trying to understand. And where the whole thing breaks down is that time's not causal, right? Time's, as an x variable, it is what it is. So the question is, what's the point to it? Well, there are 2 points to it, both of which we're talking about. The first is prediction, or forecasting. In time series, I use the word forecasting a lot instead of prediction, because forecasting builds in this idea that I'm going to learn about the future, all right? So the first reason you build models at all is for forecasting. And it's a very important need. I mean, pretty much every day the government puts out forecasts on, you know, labour force statistics or interest rates, or you name it, right? There's a whole bunch of forecasts that come out of time series models that the ABS develops. And, you know, the ABS uses the same primary methodology for forecasting that we're thinking about here. They use trend seasonal models, okay? They deal with dependence probably in a deeper way than we can in this course, but trend seasonal is where all the prediction comes from. As we've talked about, the dependence model doesn't do much at all for prediction. It just tells you how dependent the data is. So then the question comes up, well, why do you fit dependence at all, right? Why don't you just fit the trend and seasonal, and who cares if the errors are autocorrelated? Well, here's why you care. If you have extreme autocorrelation, right, and I mean extreme, by which the autocorrelation could be 1, right, then sample size means nothing. Because if you can absolutely predict from one point to the next what the error is going to be, because the autocorrelation's 1, then you don't need to collect data point after data point. The fantasy on which prediction is based is that every new data point brings new information, right? That's true when your data are independent. When you have independent data, every new data point brings a quantum of information equal to that the previous data point brings, okay? And in statistics, information is summarised through variation, all right? If you have perfect correlation going back through time, new data point, don't matter, you've already got the information, right? So, dependence corrodes sample size as a measure of information, because under independence, new data points bring new information, each one a quantum of information, all right? This is why when you think about variation in large samples, you get that root n effect, right? You know that the variance of x bar is sigma squared on n. So the standard error of x bar is sigma on square root n. And that tells you that as n grows, the variation in x bar drops, right? Which means that you get closer and closer and closer to the true mean as n grows. That only happens when you have independence. When you have dependence, that doesn't happen anymore, right? So if you can find out that the dependence is extreme, then you have a problem, and that problem essentially corrodes your ability to predict better and better by getting more data, all right? And that's why we care about dependence, and that's why we build models for dependence. The model itself is not useful for prediction. You always predict your errors to be 0, okay? So it's not a useful predictive model, the dependence part, but it's a useful model for understanding the way the series develops through time, and it's also useful for understanding how sample size relates to information. All right, so that's why we build time series models. And yes, it's different to building regular regression models for the reason of autocorrelation. All right, so that's an answer to a question that was asked. Good question. Why is this copying and pasting everything? This is so very, very annoying. Okay, so I just want to show you a simple plot here. I'm going to have to do this. Did I ever tell you I hate R? Okay. There's my... Why did it ignore type equals B? It's supposed to join the dots when I use type equals B. Goodness me. All right, I'll do it this way. Use type equals L. Okay, there's my original series. There's my original series. All right, what do we see? You tell me. So good. People getting out their fingers, some people getting out one finger, some people getting out two fingers. That's good. If you use one finger, it goes up. What do you reckon the shape is? Is it linear? Could be. Could be. Is it quadratic? Could be. Okay, could be quadratic. More than quadratic? Probably not. Okay, so trend at the moment we would think maybe is either linear or quadratic. So we'll have a look at that. All right. What about the homoscedasticity? We okay with that? Fingers don't really move further apart as you move from left to right? At least it seems so. Okay. So let's try and fit a linear trend to start with. Okay. So I'm going to centre time. It's always good practice to centre time, just makes the models fit better. And then I'm just going to add a linear. Why? Type equals B is supposed to join the dots. All right. I don't understand what R is doing to me today. There we go. Okay. Linear trend. This makes me think quadratic. Okay. And why do I think that? Linear covers the data a lot, right? It crosses over the data pretty much all the way through. But you can see here it's consistently over, in the middle it's consistently under, and at the end it's consistently over. I mean, this is the benefit of putting a reference line on a plot, right? Because when you don't put the line on the plot, you're forced to imagine the line. And in your imagination, lines may not be linear, right? Most people think their imaginations are pretty good. Generally not, okay? So you can sort of see that curvature there. I think it's worth thinking about putting a quadratic through, so let's do that. That's the dotted line. Okay, can you see the dotted line? Maybe I should have made it red. Let's see if I can make it red. Okay, there's the dotted line. You see that seems to follow the data a lot more faithfully. So I think a quadratic's going to be likely to be the thing to do. By the way, this series has frequency 12, right, measured monthly. So we should be able to use STL in order to think about this. So let's do that. So there's the STL command. And you can see it's using a low S curve, of course, here. And it's looking fairly quadratic. A little curvature to it. Another good question that was asked yesterday was, how come you're always just fitting linear and quadratics and you're not putting the low S curve necessarily on anymore? Reason is we prefer to fit polynomials for prediction. Low S for prediction is not very good. So if we think we know the shape, the low S curve is at best going to just confirm that. Nothing wrong with putting the low S curve on. When you're doing the assignment, you probably will want to put the low S curve on because maybe the shape doesn't look simple enough for you to think about the quadratic up front. Okay? So in the examples that I'm talking about, absolutely feel free to put the low S curve on, but you don't have to, right? There's no have to in modelling, as you well know. All right, so again, this confirms pretty much what we thought. Now, is there a seasonal effect? So, homoscedastic, quadratic trend, we now move to seasonal. Is there a seasonal effect? This is where you all shout yes. This is where you all stay completely silent. Okay, let's do that. all right. Yes, there's a seasonal effect. Okay. Everyone seems very subdued this morning. Big night? No? Okay, no. Not going to talk to me about anything. All right. That's very nice. Okay. So, how do we set up our seasonal thing? Okay, well, it's January through December, right? So, we're going to fit a separate constant for each month. Simple way to do that. This data set's wonderful because it starts in January and it ends in December, and you have 32, I think it's 32 full years of data, okay? To find out how many data points you have, you just use the length of the series divided by 12. That'll give you how many full years of data you have. Okay, so we're going to set up our seasonal factor here, okay? We're going to fit that into the model so you can see my model is a linear model that relates CO2 to time squared, and my factor. Okay, I'm actually going to fit that with LM. I'll tell you why in a sec, because I want to have a look at it. So there's my model. So my intercept's 322. My coefficient of time is 1.018. Coefficient of time squared 0.012. Oh, by the way, people always say to me, gee, the coefficient of time squared is so small. That's because squares of numbers tend to be big, so the thing you're multiplying it with is big. So we should talk about big and small in a second. This is February, March, April, May, June, July, August, September, October, November, December. Okay, so when you look at those constants that are fit for each season, they all look different, right? So I think we're good to fit this model. It's always useful, once you fit the model, to have a look at a summary. If you've used RLM, you won't get the summary that you want. If you use LM, you do. So let's have a look. I'm just going to make this even a little bit wider because I want to get these. Oh, the p-values won't. They're too big. Okay. All right. All good. So there's my estimates there. Before anyone asks me about what this means, this scientific notation. Okay. 3.221 E plus O2 means 3.22 times 10 to the 2, which is 100. That E plus O2 tells you where to move the decimal point. So E plus O2 says move the decimal point 2 spots to the right. E minus O1 means move it 1 spot to the left. Okay? Now, if you know what scientific notation means, you're going, why the hell is he telling us this? That's so obvious. If you've never seen scientific notation before, you're going, what the hell is he talking about? So that's why I tell you, okay? Okay, look at the t-values. You can see all of the t-values look significant. Okay, in particular, what I'm looking for here is the t-value for the quadratic term. So if you do fit a polynomial and you want to know, are those higher order terms significant, look at the summary of your fit, okay? And see whether the p-value for that term tells you to keep it or not, right? So if you're sitting there and you're going, oh, look, I think it's a quadratic, it might be linear, I just don't know. Well, you've got multiple pieces of evidence that help you make that decision. The first is your eyes. You see curvature, right? The second is what the test tells you, right? So you've got a test here for whether or not the quadratic term is needed in the model. The t-value for that test is 43. The p-value is 2e minus 16. That's 0.0000000000002. That's small. Did I miss one? Damn. Proof Michael cannot count to 16. Oh well. It's not a skill you use as a parent, right? When you're a parent, you do an awful lot of, I'm going to count to 3. But if you ever find yourself counting to 16, your kid's gone, right? It's like, I'm not sticking around for that. So, very small p-value, means it's significant, all right? All the monthly terms look significant as well. Now, I'm going to show you something that's going to make you think, Then I'm going to tell you we're not going to do it, okay? So, remember we used, this mouse is driving me nuts too. Remember when we used the STL? Here's the month plot from STL. Okay, these are the seasonal. Right. Sorry, the mouse won't track, so I just needed a good thrashing. Okay. Still won't. Oh, maybe I've broken it now. Oh well. Okay, these are the seasonal constants. So now, okay, let's think about this. This is some open air thinking. We fit a separate constant for each month. That looks like the right thing to do here, right? Because all of those flat lines are in different spots. Huh? Now, that's going to give us a model that's got 11 parameters, right? You've got a baseline, which is January, and then you've got February through December, so 11 parameters. This is going to be okay for this data. This data set has 384 data points, right? So you fit 12 extra parameters. It's not a huge problem. You've got plenty of data. But have a look at this plot here. What do you think? Tell me what you think. What do you think?
It's increasing for the first few months, then decreasing,
Yeah.
and increasing.
So it's got a pattern to it, right? It's got a pattern to it. Yeah. What do you reckon the pattern might be?
Linear.
So we've got a couple of guesses. So it looks like it could be a polynomial. This goes up, down, up, and sinusoid. Sine or cosine. Probably, I mean, if you think about this, right, it's probably a sinusoid, okay? Now, if you could fit a sinusoid, we're not going to, because that takes us into nonlinear modelling and how many weeks do we have left, right? So we're not going to fit a sinusoid. But if you wanted to, how would you do that, is the question. So you'd have to construct, how many parameters would you need to estimate? Who can tell me? Is it 1? 2. An amplitude and a frequency, right? The sinusoid's going to have a scale, that's the amplitude, and it's going to have a frequency. How often does it repeat? Okay. So it's possible to do this. As I said, we're not going to do it, because if I start talking about nonlinear model fitting, we're here for another whole semester. And you're probably tired of this, right, at this point. Christmas is coming. Let's deal with that first, right? So, we're not going to go there. But this looks like you could fit a sinusoid. Now, if I could, I would, because I'd be adopting a choice where instead of using 12 parameters, I'd be using 2, right? Big saving. If I had, maybe 100 data points instead of 400 data points, I'd probably want to go there, because smaller models are better, generally, okay? So what are the upsides and the downsides of this? Well, fitting a separate constant for each season is not wrong. Clearly not wrong, okay? But it's a big model. Fitting a sinusoid, also, it's not clearly wrong in this case. It's not clearly right either, because you don't have a lot of information to support that this is sinusoidal. You get a little bit. And it does build in a structure that may not comport with a physical model. So, if this analysis mattered and I needed to get this data analysis, as good as I could get, what should I, as a statistician, now do? Right? Answer. Stop just talking to myself as a statistician and thinking about issues of fit and issues of model size, and go talk to a climate scientist, right? So here's everything that's wrong with science on this planet. We don't talk to each other, right? The physicists don't talk to the chemists, and the chemists don't talk to the mathematicians. No one talks to the mathematicians. No one talks to the statisticians. They just give us the data and say, what's the answer? And we're supposed to go, well, here's the answer, right? And this is not how science should proceed, right? So the next step should be go talk to a climate scientist. Ask, look, is there a physical model that underpins this seasonal behaviour that I'm seeing? And if the climate scientist says, oh, yeah, we use sinusoidal models all the time, then yeah, you go, you fit it, right? You say, well, okay, I can give you an answer to the sort of model you want to fit, okay? And it's very important to have those conversations. Yesterday, did anyone get frightened yesterday? You should be. Did you get frightened yesterday? The climate change scientists released a report. Did you see what it said? If we don't stop using coal by 2030, we're all dead. Meanwhile, Trump says, let's use coal. ScoMo says, let's use coal, right? All the countries that have the coal are going, let's dig up more coal. Let's burn that stuff. Oh my God. We're in trouble, folks. We're in trouble. understanding time series models is going to be important, but we'll all be dead, so it's not going to matter. Oh boy, oh boy. So, my God. So I got scared yesterday, and I got a lot less longer to live than you do, right? I mean, I'm in my 50s, so by 2030, let's see, in 20, oh yeah, I'll be 70. What do I care, right? I'll be sitting in my backyard burning coal, because that's what 70-year-olds do. You guys, you'll have little kids, and it's scary. It's scary. It's awful. Anyway, so sinusoidal, okay? By the way, if you are doing the assignment and you see stuff like that and you want to fit a sinusoid, I ain't one to stop you, all right? Probably wouldn't do it for this project, this assignment, because I don't think there is one, but anyway. I want to encourage you to feel free to fit what you see, okay? All right, so we've gone ahead and we fit a trend seasonal model. Let's have a look at the residuals from that and see what we see. So this is the residuals from the trend seasonal fit. There they are. Okay, they look irregular. So what's gone now is that regular series, that regular wiggling. Okay, that's all gone. One of the things that people always worry about when you look at time series, when you look at the residual series, you often still see wiggles, and you want to keep on fitting them. This is irregular because as you count from peak to peak, the number keeps changing, right? So that's the challenge. So we're going to have a look at the Box-Jenkins identification for this and see where we get. So let's do that. All right, where are we? Okay, there's the ACF, there's the PACF. What do we think? What do we think? What's the first thing we think? It's not stationary, it doesn't look stationary. So the ACF appears to be damping down to 0, but pretty slowly, okay? Do we reckon it'll ultimately get down in between those two lines? What do you reckon? Yeah, I'm getting the thumbs up, that's awesome, right? So yeah, it will. So it is going to go down to 0, but it's going a bit slower than we're happy with. This is an example of what I would call borderline stationary, okay? It's not clearly non-stationary, but it's not clearly stationary either. So this is on the borderline, right? Sometimes you see patterns where the thing just doesn't damp down at all, and you know that thing ain't ever going down to 0, right? That's a big problem. This is a borderline problem. Okay, so we're going to have a choice to make here. Have a look at the PACF. What do we see? Spike 1 is outside. Spike 2 is outside. Then it bubbles away. Looks like spike 9 hits the line, but not quite. Looks like spike 21 hits the line, but not quite, and so on. Maybe spike 26, okay? But basically it looks like after 2 it dies, pretty much. So that's suggesting an AR2. So, choice number 1, fit a quadratic trend, constant seasonal, followed by an AR2, and see what happens. That's choice 1. Choice 2, go back to start, difference your data, and look at the whole thing again. Okay? So those are our 2 choices. So let's run down choice 1. Let's go ahead and fit that AR2. So we're going to rake mod dollars resid. Okay. It's going to take a while. There's 400 data points. The hamsters inside the computer here are running as crazy as they can. There we go. We want an AR2, so we want fit AR dollars coef second column. So my coefficients are 0.718 and 0.206. So my model for dependence is going to be xt equals 0.718 times xt minus 1 plus, sorry, that was a minus sign in front of that, wasn't there? Minus 0.718 times xt minus 1 plus 0.206 times xt minus 2. That's my dependence part. My main model is CO2 equals, and you've got quadratic trend. I'm not going to type it all out, you'll kill me. Can't spell. Plus, you know, constant seasonal. Fingers aren't working. Plus xt. that's how you would write it. And you fill out all those coefficients. Again, too much to type. Okay, now, once we've got that, how do we know if we've solved the problem? What we do is we look at the Box-Jenkins identification for the residuals from an AR2, which is in fit AR dollars resid second column. Okay? So these are the residuals from an AR2. Now look what happened. The ACF now completely behaves itself. Okay? And the PACF, it's got spikes all over the place, but they're all close to the line, right? So I think we've got everything we're going to be able to get here. So I look at that and I go, yep, probably okay. And again, when you look at those, the PACF, you want to fit the smallest model you can. No one in their right mind is going to fit an AR12, right? That's just silly. And God forbid you should fit an AR25. If anyone fits an AR25, I'm going to, I don't know, send the boys around to... I don't have boys, it's all right. You don't have to worry. Okay, so not much going on there. So, choice one was, we think there might be a problem with stationarity, but after we go ahead and fit the model, it goes away. So, probably good enough to go at this point. Okay? So there's my first model. All right, how would I deal with this in the second model? First of all, I'd go diff CO2. I'd create first differences. I'm going to call that Z. Okay? So Z's a time series as well. There it is. How do I proceed? Well, let's have a look at it. Let's plot Z type equals L. Oh, I hate R. There it is. Okay. What happened to the trend? It's gone. There's still a lot of those wiggles, right? It's a bit scrunched up, but if I spread it out a bit, you'll see it a bit better. And if I make it a bit narrower, if I can. Low. Won't let me drag. There. So you can still see there's still highly regular behaviour here, right? Again with frequency 12, okay? So what's the length of Z? 467, okay? 467 divided by 12 doesn't quite go, right? Reason? I used to have 39 full years of data. Now I've got one less than that because when I take differences, first one disappears, right? First one disappears. So when I set up my seasonal factor for this, I'm going to have to take that into account. Okay? So let's use H equals STL of Z, S dot period equals true, S dot window equals periodic. What am I doing? T dot window equals, I don't know, 99. Okay? Let's plot that. Plot H. I'm going to have to resize my window like crazy. All right, what do we see here? Well, look at the stupid trend it fit, right? What do you reckon? Well, we'll talk about that in a second. There's certainly seasonal behaviour here. There's the irregular component. What do you reckon this looks like, apart from a mess? Let's jack that T window up, see if we can make it look more sensible. It's a bit better. What would you fit here? What are your choices? Everyone's really quiet. So, it was a quadratic. The original data had a quadratic through it. What should happen when I take a difference? Linear. Should turn linear, right? Should turn linear. So, and this here looks kind of linear. That's a low S curve. Yeah, it's got a little bump in it, but linear probably covers that off. So we could go linear trend here. Here's another suggestion. Have a look over here, right? Have a look at this here. See how big that is and see how small these are? What's the slope of this line? Really, really small, right? So the window's designed to make it look like it goes from lower left to top right, but that whole thing fits right in this little sliver of this plot here. Okay, so an alternative to linear would be to fit no trend, flat trend, right? So you've got choices here, okay? You've got choices. So let's fit a flat trend and see how we go. So mod 1 equals mod 1 equals Lm Z tilde time CO2. We're going to have to remove the first element. Okay, removing the first element because the differences have one fewer. Okay, mod 1, a summary of mod 1. Okay, you can see it's really these windows. Let's make it bigger. So I fit a linear trend. Okay, now have a look at this. The coefficient of time is 0.00187. It's got a standard error of 0.005. Its t-value is 0.376. Its p-value is 0.707. What does that tell you? You don't need the linear term. Okay? So I'd probably fit a flat trend. How do you fit a flat trend? Two ways. How do you do it? How do you fit a flat trend? All right, let me ask you, I'm going to put the original plot back here. There's my data. Okay, where should the line go? If I'm going to fit a flat trend, where would the line go? So 0 is one suggestion, yeah? It'd be flat along here, right? Is 0 the right thing to do? It's close. You'd use the mean. Use the mean. So to fit a flat trend is really easy. There's two ways to do it. Simple way, what's the mean of Z? 0.104. So that's your model at the moment, 0.104. Okay? The other way to do it would be, instead of putting Z tilde time, you put Z tilde 1. That'll fit a mean as well. Same answer. Okay? So we're just going to fit a flat trend. So no trend means flat trend, means fit a constant, means fit a mean. All right? So let's put that on the table. All right, what about my seasonal factor? Okay, now this time we're going to be a little bit more careful when we set up my seasonal factor. V is going to be factor. It's then going to contain 2 through 12, because I'm starting in February now. Took first differences, right? So January disappears. Start in February, okay? Then I'm going to have 38 full years of 1 to 12. That's going to be my seasonal factor. Okay, so it looks a little bit different than before. Remember, before we just said 1 to 12, 39 times. Okay? Now we're going to have 2 through 12 for the first year because the differencing removed the first element. Okay? And then on. Okay? How do I fit the factor? I go mod 2, this is my trend seasonal model, Z tilde V. You don't need to put the 1 in anymore because the intercept's automatic, right? And it fit. So I got the length of that factor right. Okay, if I got the length of the factor wrong, you'd get an error, which would say, actually I don't know what it would say. Let's get it wrong and see. Let's get it wrong and see. It's always fun to play this game. Error in model.frame.default. Formula is Z tilde V. Drop dot unused level equals true. Variable lengths differ. Right? So an error that only a mother could love. Okay, so this is a trick. If you're going to use differencing, be careful about the length of the vector you end up with. It will be 1 less than the original length. Okay, and that's going to cause errors if you just don't know that. All right, so just be aware of that. The most common email I get about differencing is, why do my commands no longer work? Because the lengths don't match. The answer is, the differences have length 1 less. All right? Something to remember. All right, so I fit a trend and I fit my seasonal. What's left? Let's plot time of CO2 without the first element against mod $2 resid. Oh, type equals L. There's my residual series, okay? So it should look flat. It shouldn't look like it's got that repeated structure. This looks fine. Now let's do a Box-Jenkins identification of it. Ident mod $2 resid. It's a thing of beauty. It's a thing of beauty, if you like that sort of thing. So, what about the ACF? What's it telling me? I'm hearing people go, which is code for stationary, yes? Yes, when I want to say stationary, I usually just say and hope people understand me. No, that never works. Stationary, okay? How do I know it's stationary? The ACF collapses, stays within the train tracks all the way along, collapses quickly. So I think my difference series is stationary. PACF says fit what? AR1. AR1. Now that makes sense, right? If you're fitting an AR2 to undifferenced data, you're probably going to fit an AR1 to difference data. That's how the differencing affects the model selection. So let's do it. Fit AR equals rake of mod $2 resid. Twiddle thumbs while it does it. There we go. And we want an AR1, so we want fit AR $coef first column. So the coefficient is minus 0.23. All right. And let's have a look at the residuals. Ident of fit AR $resid first column. And there you see the ACF behaves itself and the PACF has no structure. Okay? Again, a habit that I want you to get into is when you look at the PACF, if you see spikes at long lags, so a long way along, that just poke above the line, ignore them. Right? Ignore them. I've got at least 3 reasons you should ignore them. All right? Want to hear the 3 reasons? I guess that's a no. All right. You do? Oh, good. I love giving reasons. Okay, the first reason you should ignore it is it's inconvenient. Right? If you fit a long-run AR model, it's only going to enrage the person who's marking your assignment. They're going to go, didn't Michael tell them not to fit long-range AR models? Etc., etc. So that's reason number 1. So that's a purely practical reason. Reason number 2, this is a statistical reason. This actually is a deep one. You know, we look at each of these spikes and we go, is it inside or outside the dotted lines? And so what we're intrinsically doing is we're doing a test for each spike. Is it significant? We're asking, is the first spike significant? Is the second spike significant? Is the third spike significant? And we're doing this all the way out to 26 spikes, right? We're doing 26 consecutive tests on the same data, each at 0.05, right? So there's a 5% chance the first one's wrong. There's a 5% chance the second one's wrong. There's a 5% chance the third one's wrong. What's the probability that one of them will be wrong? You don't need to give me a number, you just need to tell me whether it's going to be big or small. It's going to be big, right? This is called the multiple testing problem, right? I'm doing 26 tests each at 0.05. The chance I'm going to get one of them wrong is very high. It's actually over 90%, okay? So if you see a spike at a long lag that's outside the dotted lines, it's probably not real. It's probably not real because you're not testing it at the level you think you're testing it at, okay? All right, I had 3 reasons and I've forgotten the third one. Don't you hate that? But everyone knows it happens, right? You go, oh, I've got 400 reasons to tell you, and then you're going to get to 399. I've forgotten the last one. Anyway, the second reason was the most important one. Multiple testing is a problem, okay? And so we've now got a second model that we could fit. Okay, so what's my second model look like? My second model looks like, let's write it down, because I think it's important to know how to write down a difference model. Diff of CO2 equals a constant, was 0.1048 or something like that, my constant, plus some other constant, I'm going to call it C1 because I can't remember what it was, times an indicator that I'm in February, plus C2 times an indicator that I'm in March, and so on, ... You know how the rest of the year goes, okay, plus XT, okay? So it's difference series equals structure plus irregular. Now I don't write diff irregular, I just write XT. XT means what's left over. The second line is XT equals, what was the number? Minus 0.23 times XT minus 1. All right? So that's how you write down your model. Now it's okay to leave it like that, but I would prefer if you did this. CO2 at time t minus CO2 at time t minus 1 equals 0.1048 plus ... plus xt. I mean, they're the same. A difference means now minus last month. Okay, that's cool. But again, remember the point of writing out the model. You're not writing out the model for you. You're writing out the model for the person who's reading the report. And you don't know, you know, so you might be, next year, you might be working for you might be working for one of the big four. And this might be a report going to the CEO. The CEO is 70 years old. He earns $17 million and he can't remember how to take first differences. But he does know what a good glass of scotch tastes like. You know, so you can't expect necessarily the people who are reading your report to understand diff. They'll go, diff? What's diff? Right? So spell it out for them. Remember, communication means being clear. So spell it out for them and write it like this. Okay? So I generally write it as two lines, the first line being this difference here, the second line being this difference here. Okay? Then you're done, apart from the residual plots that you must always produce, you know, residuals versus time, check for heteroscedasticity, all that stuff. So I'll leave that to you. One thing I should say about those final residual plots, residual plots are not display graphics. They're not graphics you show to anybody apart from yourself and me, right? In no report on God's green earth should residual plots be shown. Shareholders don't understand them, CEOs don't understand them. They're for you. They're an analytical tool. They're not a display tool. Why do I get you to produce them here? Because I'm your audience, right? Not the CEO. I'll never be a CEO, right? Ever. I'll never earn that much money. It's just crazy. Anyway. I often ask my bosses at ANU, where's my Christmas bonus? And they say, isn't it sunny outside? I change the subject. And I go, but how? You destroyed campus, I say. I have to walk through rubble every day. They say, but isn't that sunshine lovely? Anyway, yeah, these are the conversations we have at the ANU. All right, now, okay, before we leave this, two models, okay? First model, series on the original scale, quadratic trend, constant seasonal, AR2, right? That's model one. Model two, differenced series, no trend, so flat trend, AR1, okay? Which one? Now, both are okay. Let's be clear. Both are okay. If I had to choose one, which one would I choose? The first one or the second one? And why would I make that choice? Second one? Heard someone say second. Why? Why did I do that? Because
Always better to use the differences.
Why? It's smaller. Slightly smaller model, right? So, you know me, I have a preference for slightly smaller models, right? So I'd probably go with the smaller model. Now, if you chose the first one, that's not wrong, and there's a defence for doing so, right? The defence is prediction is trivial, right? Prediction is